Well, hi everybody. Just decided to get even a little bit further ahead with you all by putting together this hopefully fairly short video about section 8.4 of the book. This is going to be great if we can kind of knock this out quickly. Then we aren't going to have that much left to do this coming week in class. So that'll give us more time to practice and do questions and get ready for the final exam coming up. This section is called Improper Integrals. And just to set the stage for that, let me just remind you that up until now in chapters 7 and 8, we've been computing a lot of definite integrals. So here's the expression for that, which you guys have all seen before. We just integrate from a to b of f of x dx. This is some closed interval from a to b here, right? We're finding, the total area under the graph of f of x between a and b, for example. That's one of the things that we've done. But it turns out that sometimes there are other intervals that we might like to consider besides just closed intervals from one number to another. To kind of explain where that might come up, I wrote down this nice example here to kind of get you set up for that. Okay, so suppose that we had a radioactive substance that was entering the atmosphere at a certain rate. Okay, so I'm giving you the rate at which this waste, this radioactive waste, is entering the atmosphere at any given time. So this is a rate of change of the amount of this substance that's in the atmosphere, right? The question is to find the total amount of waste that enters the atmosphere over all time. Over all time. Over all time greater than or equal to 0. Right? The way that I would want to answer that, right? Remember that the total amount of something is just the integral of the rate of change of that expression. So I could write it like this. Okay, this is just my rate of change function, f of t. But what I would want to do here, guys, is I would want to integrate that starting at time 0, but over all time would actually mean that I'd never stop calculating the amount of waste that's coming into the atmosphere. I go all the way to infinity, right? When you have an integral where there are limits of integration that involve infinity, we call those improper integrals, okay? And believe it or not, we can actually calculate these things as well. The main difference here is that it's possible that when you calculate an improper integral, you could get an answer of infinity. It might not be a finite number. When you do this integral right here, right, of course you're going to just take an antiderivative and evaluate it at the upper limit and lower limit, right, and subtract. That's going to be some number, right? That's going to be a particular number. These kinds of integrals, these improper integrals, can actually fail to exist. They can actually give you values that are not numbers, okay? I'm going to show you in a minute, right? I mean, you can't really plug in infinity. I can find an antiderivative here, but plugging infinity into an antiderivative is actually something that doesn't really make sense. So let me talk a little bit more about how we would handle something like this. And here's this example kind of shows you where it might come up. Okay? Now guys, I promised you that if you watched my videos, you might get a chance to get a little extra credit. So I've got a couple of things that I'm going to give you throughout this video that you're going to want to watch for that. On the next homework assignment, when you turn it in, I'd like you on the front of your homework, right at the top, to write down the name of my cat. All right? My lovely cat. Her name is Ginger. I'll try to show you a picture of her. I'll bring a picture to show you next time. Okay? Ginger. So write that on the front of your homework assignment, and you're going to get some extra credit for that because you saw me do this during the video. Right? Okay. Anyway, so improper integrals are kind of interesting. So for example, we could have an integral from a to infinity. This is an example of an improper integral. Some number is a lower limit going up to infinity. How am I going to evaluate that? Well, the way that we're going to do that, guys, is we're going to start by assuming that we really only want to integrate from a to b. Okay? But then we are going to take a limit as b goes to infinity. This is really great because it's reviewing limits from way back in the early part of the course. We have to calculate an integral. That integral, when we evaluate it, will have b in it. So we're going to get an expression with b in it right here. But then we're going to let that b drift to infinity. And we're going to see if we get some value out of it. Okay? I'll show you an example in just a minute. Another possible scenario is maybe the lower limit is minus infinity, and we're integrating up to some value b, which is like some fixed number here. Right? Same kind of idea. What we're going to do is we're going to first evaluate the integral from a to b, and then we're going to slide that a towards, sorry, this is an a. We're going to slide that a towards negative infinity. All right? Finally, it is actually possible to have indefinite integrals with a minus infinity lower limit and a plus infinity upper limit. Whenever that happens, guys, what we're going to do is we're going to break it down into two integrals. So this is the way we would do it. We would pick some number c. C is somewhere along my real number line. And we would integrate from minus infinity to c, and then from c to infinity. Both of these two integrals are handled the way that I just described the calculations up here. Now guys, we know full well that limits do not always exist. That is why it is possible that these kind of improper integrals may not have values. Okay, they may not give us a nice round number. So we do have to kind of watch out for that. Okay, let's do some examples. Let's suppose that I wanted to integrate from minus infinity to minus 1 of x to the negative 8/3 dx. Okay, this is an improper integral. But what I can do for that is I can take the limit as a goes to minus infinity of the integral from a to minus 1. Right? That's exactly this kind of a structure right here. Okay? A goes to minus infinity, a up to negative 1. All right? We're not going to evaluate this limit right away. Before we do this limit, we have to calculate the integral. Okay? I'm going to use the power rule backwards. I'm going to jack the power up by 1. So if I add 1 to negative 8/3, I'm going to get negative 5/3. And I have to divide by negative 5/3, which is like multiplying by negative 3/5. Okay? This has to be evaluated from a to negative 1. Let's do that evaluation step right now. Limit as a approaches negative infinity. I'm going to put in negative 1 here. Now, negative 1, if we take the cubed root of negative 1, we just get negative 1. And the fifth power of negative 1 is just negative 1, right? So we have negative 1, and then the minus flips it over. Well, 1 over negative 1 is still negative 1. So I have a minus sign and a negative 1 and a 3/5. That's all just 3/5. Okay? That's for the upper limit. For the lower limit, we have to subtract what we get when we plug in a. Now the first thing is there's a minus here already, so it's going to change the sign of this thing. We're going to get a 3/5, and then we're going to get a to the negative 5/3. Okay? Now, here's the thing. This negative power of a is really on the bottom of this fraction. And when you take a huge number, right, a huge negative number in this case, and you take the cubed root and the fifth power of that, you still have a huge negative number. In fact, you might even prefer to think of this like this. The a to the 5/3 is down here, right? You put a huge number down on the bottom here, this whole part of the expression is going to go to 0 when I calculate this limit. The only thing that doesn't go to 0 is this 3/5 that's up here in the front. Okay, so that would be the answer. It's amazing. Okay, we are integrating over an infinite domain here, right? The domain, the interval is minus infinity to minus 1. Goes forever, but we get a finite value out of that integral. Let's do another example. Okay, let's do one more that's pretty easy, and then we'll try a couple that are a little bit harder. Let's do the integral from 1 to infinity of 1 over x squared dx. Okay? All right, So for that one, we're going to take the limit as b goes to infinity of the integral from 1 to b, and I'm going to write this as x to the minus 2 so that I can get ready to use my power rule. My power rule backwards on this is going to be the limit as b goes to infinity. X to the minus 1 over minus 1 can be written this way. Right, that's the antiderivative. I have to evaluate it from 1 to b. Okay, I'm not calculating the limit yet. I'm not calculating the limit. I'm just plugging in the upper and lower limits here. So negative 1 over b right now is the upper limit. And then I subtract negative 1 over 1. So we get an expression like that. As b gets really, really big, this first part becomes like 0. Yeah? So the answer is 1. What you need to understand, guys, is what you're really saying. What you're really saying here is that if you graph 1 over x squared, there's the graph, and you start calculating the area under this graph. Keep in mind, this goes forever to the right, yeah? This seems to go forever over there. But if you wanted to paint this shaded area, you would only need to buy 1 unit of paint. Even though the region goes forever to the right, the total area under that whole entire graph, forever to the right, only adds up to 1. It's kind of counterintuitive. In some ways, it doesn't really make a whole lot of sense. But improper integrals are like that. They can be a little bit counterintuitive. Okay, guys, for your next little extra credit, I want you to write down the type of car that I have now. It's my brand new car I got last year. And if you put this on the top of your homework assignment, okay, the top of your next homework assignment, I now have a Toyota Corolla. All right, put that down, you'll get a little extra credit. Okay, let's do another example. Let's do the integral from 0 to infinity of 50 e to the negative 0.04 t dt. You remember this one? This is the total amount of pollution from the radioactive decay of that substance in the example that I showed you at the beginning. Okay? So this is going to be the limit as b goes to infinity of the integral from 0 to b of 50 e to the negative 0.04 t dt. Okay, so we put the limit of b up here. Then we're going to take the limit as b goes to infinity at the end. So here we go. To do this antiderivative right here, I'm going to pull the 50 out. This is just e to the at, right? So if you remember, we have to divide by the a, and then we just get e to the negative at again. We're going to evaluate that between our two limits. All right? So we have 50 divided by 0.04. Somewhere I calculated that. 50 divided by negative 0.04 is negative 1,250. All right? And then we're going to take the limit. So I'm just pulling that constant out in front. Okay, so 50 over negative 0.04. I'm just putting it out in front here. We still have to take the limit as b goes to infinity of e to the negative 0.04b minus e to the 0, which is 1. Now, as you let b go to infinity, this is e to the negative infinity, right? Negative huge power. That's like 0. You actually have 0 minus 1, which is negative 1, and negative 1 times negative 1250 is 1250. It's a finite amount of total waste. It's a finite amount of pollution. So it's quite remarkable that you can actually get a finite value out of that. Okay? Even though that substance is decaying radioactively forever. It's doing that forever. Okay? All right. Let's see. Let's try another example here. Let's do let's do the integral from 2 to infinity of 1 over x ln of x dx. All right? Let's try this one real quick. This one is, of course, an improper integral again. We're going to take the limit as b goes to infinity of the integral from 2 to b of 1 over x ln of x. And we're going to calculate this integral first. It's going to have b in the answer, and then we'll think about b going to infinity. To do this integral, now this one we need a u substitution, right? So I'm going to let u equal the ln of x, and the derivative of that is 1 over x, which gets multiplied by dx. So you actually have the whole thing right here. It's really just 1 over u du, right? So if we do this expression then we're going to have the integral from 2 to b of 1 over u du. And the antiderivative of that, oh actually, I'm sorry. Remember that when we switch the variables here, I usually just drop these limits of integration while I'm doing the calculation. So there isn't really a b here at the moment, but I'm still going to write limit as b goes to infinity, so I don't forget to do that. But it's going to be the ln of the absolute value of u, and then I'm going to go back and put in what u is, which is the absolute value of x. And now that we have to evaluate from the original limits here. Okay? So this is going to be the limit. Let me take off this so it doesn't get in the way here. This is the limit as b goes to infinity of the ln of the absolute value of the ln of b minus the ln of the absolute value of the ln of 2. Alright. Well, this is just some number right here. I don't know what it equals to. You could get a calculator and take the ln of the ln of 2. But this one, as you put b to be a huge, huge number, the natural log of a huge number, if you think about the graph of the natural log function, it blows up, right? As x gets big and you look at the ln of x, you go out this way, it blows up to infinity. This is infinity, guys. As b goes to infinity, you get infinity here. And subtracting some small number from infinity is still infinity. We say that this diverges. This integral diverges. It doesn't have a finite value. If we wanted to paint the region of this function underneath the x-axis forever from 2 to infinity, we would need an infinite amount of paint to be able to do that. We can't do that with a finite amount of paint. Okay? Right. Let's do another example. Hopefully these are making sense so far. A couple more examples maybe. Call it good. All right. Here's an example. So sometimes you'll get infinity or minus infinity or something like that. Those just diverge. It's not really a number. Okay? It's not really a particular value. It's a limit that really didn't exist. You remember whenever we get a limit of infinity or minus infinity, we just say it doesn't exist. It doesn't really exist. Let's do this one. The integral from 3 to infinity of 1 over x plus 1 cubed dx. All right? Let's try this one real fast. To do this one, I'm going to also use a u substitution. I'm going to let u equal x plus 1, right? So du is just equal to dx. And this is going to be the limit. Let me just write this way. This is the limit as b goes to infinity of the integral from 3 to b of 1 over x plus 1 cubed dx. And I'm going to just, at least at the beginning here, I'm just going to treat this as an indefinite integral of u to the minus 3. Okay? My power rule backwards comes into play now, and I get u to the minus 2 over minus 2. So I'm going to write it this way so that I have it as a fraction. It just helps me to think about it a little bit better. And then I need to go back and put in the original expression for u here, which is x plus 1 squared. Okay? This has to be evaluated from 3 to b. Okay? I'm running out of room, but I think I can squeeze this in here. When I plug in the b, I'm just going to take the limit as b goes to infinity of negative 1 over 2 times b plus 1 squared, and then minus a negative 1 over 2, so it becomes a plus, right? I'm subtracting a negative here. It's going to be 3 plus 1 squared. 3 plus 1 squared is actually just 4 squared, or in other words, 16. Okay? This is the thing we need to take the limit of. The first part, you see, the b is blowing up on the bottom here. When b blows up in the denominator, it makes the whole fraction go to 0. This goes to 0. And what we're left with is just the second part, which is just a number. which is 1 over 32. Okay? So that is another example. I think these are all of the examples. It's probably good enough for now, the examples. Let me give you one more thing to write down for a little bit more extra credit. All right? Because you've been very good and watched this whole video. The hardest 14,000 foot mountain in Colorado. I love climbing 14,000 foot mountains in Colorado. So write down on your homework, on the top of the homework assignment, the name of that mountain. You can see a picture of me on top of that on the front of my webpage. All right? Capitol Peak is the name of it. All right? So you've had a few things to write down throughout this video. And hopefully you also learned a lot about how to evaluate improper integrals. We're going to have homework on this that you're going to turn in this week on Tuesday. I'll be happy to practice with you and help you a little bit more with these as we go forward. But hopefully this makes sense. It's really not any new material. It's just that we're putting a couple of things together. We're doing integrations, definite integrals, but we're putting variables as either the upper or lower limit of those integrations. And then we have to deal with taking limits as those variables go to infinity or to minus infinity. All right? Hopefully it all makes sense, and I will see you guys soon. Thank you very much for your attention this evening.